So in this example, a researcher wants to see if a weight loss program is effective. She measures the weight of 6 randomly selected women before and after the weight loss program, and it asks to find a 95% confidence interval for the mean weight loss program. So the first step of every problem is to determine if you're going to be doing a confidence interval or a hypothesis test. So I look for very specific words. In this case, it actually says the word confidence interval, so I know I'm doing a confidence interval. Next step is to figure out if we have one sample or two. So I do notice it talks about women before and after, and I notice that there are 2 sets of data. So that tells me it's a 2 sample. And then the other thing I need to know, is it a proportion or mean? I happen to, in this problem, actually see the word mean. And the last thing is, since it is 2 sample, I have to ask myself, is it paired or independent? Since I use the same women before and after, that means this woman's weight does in fact affect this woman's weight, so they are dependent on each other. So this is a dependent sample. So we can actually say this is a 2 sample paired t-interval. The first step of every confidence interval is to state the random variables and parameters in words. You do have 2 things you measured. You measured the weight before, and then you also measured the weight after. So we would have a weight of a woman before the weight loss program and a weight of a woman after the weight loss program. Call one X1 and the other one X2. It does not matter which one you do. Everything comes out the same in the end. It's just some signs are switched. So it's up to you. Then since we are doing mean weight, we would have the mean weight of a woman before the weight loss program and a mean weight of a woman after the weight loss program. If X1 is before, then mu1 would be before, and X2 is after, mu2 is after. Since this is a paired test, we actually are be looking at the mean difference. Which is not technically, but can be thought of as mu1 minus mu2. Okay. The next step of every confidence interval is to state and check the assumptions. So a paired test or paired interval has 2 assumptions. One is that you have a random sample of pairs. So we are looking at these weights being collected as pairs. So it's not really a 2 sample anymore. It really is 1 sample, but you collect them in pairs. So we have a random sample of 6 pairs of weights of women was taken before and after the weight loss program. If you look up, the problem actually says that the women were randomly selected, so we do in fact have a random sample. The second assumption is that we're actually dealing with these differences. We don't really care what the weight was before and after, we care about what the difference was. And when we talk about a paired test or paired interval, the population of those differences in the weights before and after need to be normally distributed. You don't care about each individual population of the weights before and weights after separately, you just care about those differences. So you'll find those differences first and then figure out whether or not that population is normally distributed. It's only 6 values, so we're not going to get a whole lot, but we can look at a normal probability plot. Looking at this, it does look somewhat linear. If you're not really sure that it's linear, then you can also do a histogram. The histogram looks somewhat bell-shaped, and there was only 1 outlier in the data set. So we can, from all this evidence, assume that the distribution of the differences in weights is normally distributed, and therefore all assumptions are satisfied in this case. All right, so now let's go on to actually do something. So now we can actually calculate the rest of the information. You need all that we just did to make sure you're doing the right test and to set up the preliminary information. But now that we're here, we have to actually figure out what is the calculations. Again, what we care more about in this problem is the differences. We are caring about what is the difference between x2 and x1. I'm sorry. We're caring about the differences between x1 and x2. I don't know why I said it backwards. Weird day today. All right, so we do want x1 minus x2, and d is always x1 minus x2. As a reminder, x1 was the weight before, and x2 we decided was the weight after. If you switch them around, your d's are just opposite signs. All right, so we'll make a little row here of the d's. Subtract these first numbers, you get 22. Next set of numbers, you get 21, 25, Next set gives you 24. 168 minus 152 gives you 16. And then the last one is 21. You'll now use technology. It doesn't matter if it's a calculator, R, Excel, some other statistical package. Use a technology to find out what D bar is. D bar turns out to be 21.5. S of D turns out to be 3.15. And our number of pairs is 6. In a t-test, you do need to care about the degrees of freedom. In this case, the degrees of freedom is n minus 1. So in this case, our degrees of freedom would be 5. We'll use that in a moment. The formula for a confidence interval is d bar plus or minus e. For a paired test, that e, or paired interval, that e is actually t sub c times s sub d over the square root of n. T sub c is a value that we're going to get from a table, but you can calculate it. What T sub c represents is if you look at a t distribution, you're going to have a T sub c up here and a negative T sub c below 0. 0 is the center. And this area here is whatever confidence level you want. So the area between negative T sub c and positive T sub c is the area you actually want. Let's go back to the problem and see what percent we wanted. It says we want a 90%. So that means this area here is 0.9. That's the probability, and you can use technology to calculate the negative T sub c and the positive T sub c from that. We're going to go ahead and use a table just to make life a little bit easier on us right now. So there are tables of T's around. So if you go down, we did have 5 degrees of freedom, so you're going to go down this first row to 5 degrees of freedom. Across the top, you're going to see your confidence levels. We had a 90%, so we're going to come to there. And wherever these two intersect, these two rows and columns intersect, is what your T sub c is. So in this case, it's 2.015. So now we can calculate E, 2.015 times 3.15 over the square root of 6. And E comes out to be approximately 2.6. So we're going to actually do D bar minus E is less than mu sub D. Mu sub D, again, is that mean difference we're trying to find. In this case, that represents the weight loss. And D bar plus E. So we'd have 2.6, sorry, apologize for that. We would have 21.5 minus 2.6 and 21.5 plus 2.6. So we end up doing that calculation. 18.9 is less than mu sub D, is less than 24.1. Then we can get a statistical interpretation. The statistical interpretation is there's a 90% chance that the interval 18.9 is less than mu sub D is less than 24.1 contains the true mean difference. With confidence intervals, this is the way we interpret them because the interval has a chance of actually being a correct interval. It has a chance of being wrong. There's a 10% chance that this interval did not capture the true mean out there, but we have a 90% chance that it did. So we're in pretty good shape. Now we can get the real world interpretation. Again, that mu sub D was the mean difference. In this case, it represents weight loss. So we can actually say a woman can expect to lose between 18.9 to 24.1 pounds on this weight loss program. All right.